This morning I'd like to just take a few minutes to talk about positioning and leveraging first principles analysis and modeling in general in what I hope is a pretty typical pharmaceutical company. I work for Eli Lilly and Company, we're based up in Indianapolis, and for those of you who don't know us, we manufacture a lot of insulin. We've had Zyprexa and products like that. So what's the interest here? And in a pharmaceutical operation, we have lots of different things going on. The company is very heavily driven by obviously the development of and identification of new pharmaceutical compounds. I work in the manufacturing area, and we get an awful lot of different issues and problems and opportunities thrown at us. What we've seen more recently in the last number of years is the initiative of, anybody's heard of the FDA initiative, Quality by Design. One of the things they've done in that initiative is they've really put some focus on a more fundamental understanding of the processes and the products that we actually work with, and an expectation of a higher level of understanding of those processes. So, for example, here's a document produced by the FDA, Scientific and Regulatory Considerations for Implementing Mathematical Models in the Quality by Design Framework. So, a positioning here where they're saying, this is something that we like to see, that much deeper understanding of both your processes and your products when you submit these for application for a new product application. They've also used this diagram, I think, to help us understand their position. And what this represents is a pyramid, and it's kind of like a pyramid of understanding. So you can just imagine, you can approach a problem at the very lowest level, and I like to call it, throwing darts at a dartboard. And hopefully, if you get lucky, one of them hits the center. Okay? You can approach things like that. I mean, we're told that Edison, when he discovered the light bulb, he took 10,000 opportunity or efforts to get it right. Okay? And of course, that's okay for Edison when he was living back then. We can't be taking 10,000 shots on goal for some of the things we need to be doing. So if you want to get more sophisticated, you go from that to heuristic rules, and finally up to empirical modeling. But if you want to go to the next step, you really have to think about more mechanistic-based models and first principles-based models. And the reason that the FDA likes to, in the past, has liked to use this diagram is one of their observations of the pharmaceutical industry is that we've tended to focus on the first three levels and not get much beyond the level of empirical modeling of our processes and products. So they're very interested in us gaining a much more fundamental understanding of our processes and products by building these more mechanistic and first principles-based models, so we can build better control strategies and be able to demonstrate to them that we're controlling all the right things to give them the appropriate level of quality in our products. So in this focus on the use of first principles, what we're really trying to do then is we're trying to understand our processes, improve our control strategy so that we're controlling the right thing, we've identified all the right risks, and the controls we're putting in place to mitigate those risks are appropriately designed. Obviously, improve our root cause analysis. We're not perfect, things don't always go right, and you've got to be able to identify the root causes and deal with those. And then also we want to reduce the risk from our process changes. So when we make a change, do we understand the risks we're introducing, and have we, again, managed those appropriately when we actually put those in? So when you're trying to make people do something, if you like, it's always good to have kind of management, adoption and getting them to talk about it. So our VP of corporate engineering, I work in the corporate engineering area, and our VP kind of uses this quotation. He says, the use of a first principles-based approach results in faster, better, more robust, and more sustainable solutions to problems. And this is really important, I think. It also facilitates a better understanding of why the solutions work. That's really important. Because if you're trying to get some people enthusiastic about spending money, spending their time, stuff like that, if you can really explain to them why this is the right way to go and not something else, that's very advantageous. And what we find is when we can frame things in a first principles based approach, and we're able to explain to people why you do it this way, or why it needs to be done this way, or why it's this valve or this pump or whatever it happens to be, that's much more powerful because you can really help them understand why this is the right way to go. It's easy to get lost in the mathematics of what first principles are. We all have our favorite first principles: heat transfer, mass transfer, ideal gas laws, whatever it happens to be, Navier-Stokes equations. That's the fun stuff, okay? But it's very, very useful if you can really explain to people what you're doing independently of all the detailed mathematics. What are we really after here? And so I kind of use a few things to help people. This is one of them. And I basically try to explain the use of first principles, not in a mathematical way, but in more from the perspective of what's truly going on. And I define first principles as the fundamental causal physical relationships that constrain the behavior of a process or a system. So I won't do it, but if I throw something up in the air, we're all going to pretty much bet it's going to fall back down, right? And if I do that tomorrow, it's going to be the same thing. Why is that? Well, it's because of gravity. Gravity is the first principle that constrains the behavior of this to come down once I've thrown it up in the air. It doesn't have any choice, right? It has to do it. That's gravity for you. If I threw it up in the air and it didn't come down, okay, we wouldn't throw gravity out the window, right? We'd assume there was some other effect going on that we didn't understand, right? We call gravity a first principle because it is fundamental. It constrains the behavior of a system. If you understand the first principles behind any system, it allows you to predict and explain why we get one type of behavior, it comes back down, versus some other type of behavior. And if you're not getting the behavior you expect based on your level of understanding, fundamentally, your understanding is off. You need to improve your understanding. So this is kind of a non-mathematical way we can help people to understand what we're after here and why this is important. This is another icon I use to help explain the process of implementing first principles. And everything we do, at least everything I do, is always driven by a specific decision. I don't know what it's like for you, but somebody says, I'm trying to do something. I need to decide what agitator to put in that tank so it mixes well, or mixes within 10 minutes, or whatever it happens to be. Everything is driven by some specific decision that you're trying to make. Based on that, you define a specific system that you need to work on to help you make that decision. Once you've decided on the specific system, you now apply a first principles approach to create the model. And what we point out to people here is the usefulness of this step in the process is that all of these first principles weren't invented by me, or by you, perhaps. They were invented by other people. So it essentially is a way to build on the shoulders of the giants that came before you. So when I use the ideal gas law, I don't have to spend 10 pages justifying the use of the ideal gas law. Okay, that's pretty easy to justify. Worst case, I have to make a reference to my favorite textbook. But I don't have to justify it. I don't have to justify the Navier-Stokes equations every time I use them. That's very, very useful. It's extremely useful when you can do that, when you can actually take something out and you don't have to justify it. That really speeds the process up and makes it very, very efficient. Once you've done that, we create a generic model of the system, which can take obviously many forms. A lot of the stuff here we've talked about are things like partial differential equations and ordinary differential equations, but models can take other forms as well. Once you've defined this generic model of the system, then you apply some computational techniques like you see in COMSOL or other products, finite elements, whatever it happens to be, to solve that model, to come up with some sort of generic solution. And then finally, once you apply it to your particular specific situation using some simulation of the real data that you have, you end up generating the information hopefully you need to help you make your decision. The point being here is that what you're really doing is you're taking a specific situation, and by making it generic, you make it efficient. And this is very, very important in the way we apply first principles. We want people to see that if you take this approach, you're actually being quite efficient in how you do it. And so for example, one of the tasks we have to do in a pharmaceutical environment when we come up with a new product is decide on the solvent system we need to use to work with that system, something that it can dissolve in, come out of, when we want to crystallize it and stuff like that. And we have a big long list of solvents that we can choose from. Now, if you were to go in to take a new product that nobody's worked with yet, you have no data, you've got to go into a lab and you've got to work out which of these 100 solvents is the best solvent to work with. That's a lot of lab time. And it's actually practically impossible to do. But if you use a first principles approach, you can whittle that down to a smaller number of solvents, and then that's what you take into the lab to do the final analysis. Very efficient. So we use this as a way of explaining to people the efficiency of the methodology. The other thing we're very, very careful of is, it's the old story about it's sometimes very hard to make a customer, but it's very easy to lose one. One of the biggest failure modes we have in applying this kind of work is to overpromise. It's to tell people we can solve everything, every problem they have, we can solve it using first principles, and then the next day somebody comes with a problem you can't solve. You can't do that. So we have to have a way of explaining to people why we're more enthusiastic about solving some problems and not other problems. And we use a simple icon here, simple diagram here. We basically look at it from the perspective of what's our level of understanding of the first principles involved and what's the difficulty in applying them. And depending approximately where you land on this grid is a way of explaining to people, that yes, this is a good example and we're going to get good results, or it's not such a good example. So the ideal one here is that our level of understanding is high and it's easy to do. That's utopia, right? That's where we'd all like to be. Okay? We get a lot of work done, make a lot of money for the company, and we're a hero. Unfortunately, the real world doesn't work like that. Sometimes we end up with a situation where our understanding is high, but the difficulty at the moment is very, very large. So what we will tend to talk to people about saying, we're not sure how to do this yet, but we know it can be done, so we'll try it, but you got to give us some leeway, if you like, that we might take a long time. We might have to invent some new capabilities for ourselves internally and stuff like that. Sometimes our level of the first principles is low, but it's easy to actually do something. And so we say to the customer, look, this is exploratory. We're going to try something, but don't expect too much. If we get something, great. Okay, but we go into the analysis with that expectation. We don't overpromise. And so this is a very useful way to explain to people why, as I say, we're enthusiastic about applying first principles in some cases, but not in the other, so we don't end up overpromising. The other final thing then is that we like to talk about is, when you do get good examples, we spend a lot of time sharing those examples with people so that they're aware of what's going on. Because when you're in a big organization, it's amazing, even though you've got all these fancy electronic systems for sharing information, people are too busy most times to take a lot of cognizance of those systems. So getting stuff in front of people is really the best way, and then using word of mouth after that. So basically, we've created an internal website of, at the moment, about 100 examples of different applications of first principles. And in these examples, we emphasize two things. First of all, why did you use a first principles-based approach, a modeling approach in the first place? And then what business results did you actually get? That's very important, because this isn't a theoretical exercise in keeping me in a job. It's supposed to do something for the company. And then obviously we also use internal presentations, presentation forums to try and promote these ideas. And of course we do write internal technical reports, again, so that people will have a legacy, place to go back. And so if somebody comes up with a problem, I may be able to say, well, I've solved something like that before. Go read that technical report first, then we can have a conversation. So with that in mind, I just want to give you an example of, and this is an example of applying COMSOL to a first principles case study. And I've picked this example not because it's got some fantastic, way out there first principles, but because it was actually a very effective example. Okay. Sometimes what we find is the most effective examples sometimes are actually the simplest, because the customer appreciates them that much better. So I don't know how much you know about Lilly's business, but we do a lot of insulin, and nowadays a lot of the insulin is delivered in a device. And on the left-hand side here, I've shown what we call our insulin quick pen device. And in insulins, these devices, they are multi-dose devices, and when you want to use it, you dial up the amount of units you want to take, you put on a needle, and you inject yourself with the device. These doses tend to be quite small. More recently, as Lilly and obviously a lot of other pharmaceutical companies, we've been getting into monoclonal antibodies. And for the monoclonal antibodies, the doses tend to be much bigger. And so what we've designed is a series of single-use auto-injector devices. And one of the differences between the auto-injector devices is they're spring-loaded, so when you activate the device, it actually pushes the liquid in itself, whereas these ones, you actually push it in by hand because the doses tend to be smaller. The key thing, though, is that they're both based on the technology of delivering the medicine via a needle into your skin. So you puncture the skin with a needle, and you have to something has to force that medicine through the needle. Okay, that's the key of these designs. They're needle-based drug delivery systems. Now, when you're doing that, there's two key considerations you have to think about. One is, if you think about it, you're trying to force a liquid through a needle, a pretty small needle. Now, what you'd like to do is you'd like to use smaller gauge needles to reduce the force. Smaller gauge needles, bigger inside diameter, less force to push the medicine through. Okay? However, you also have to worry about the patient experience. Imagine trying to puncture your skin with a 1 millimeter ID needle. It wouldn't be very pleasant. Okay? So there's a lot of pressure on pharmaceutical companies to make the needle IDs smaller. Okay? Because the smaller needle ID, the less pain you feel when the needle pricks your skin. So, as is the case with a lot of engineering problems, you have two things that are perfectly opposed to each other. Okay? How do you deal with that? This is a real problem for the industry. And then you start looking at the first principles and you say, okay, the old Hagen-Pazui equation, it's the design engineer's nightmare. Why? Because of that d to the fourth. Okay? You want to deliver something in a certain time, a certain volume at a certain time, okay, and you're playing around with this needle ID, you've got this d to the fourth here. Okay? Not good. Any change at all to that needle ID has a big impact on the back pressure that's generated as you try and push that liquid through the system. And you've got to remember, the needle IDs we're talking about here are in the range of 0.1 to 0.3 millimeters. So they're quite small. Right? So that's the first problem. You know, these are small IDs, so you can kind of see that the pressure, the back pressures can get very high. The other thing that's going on is there's a lot of pressure to use more concentrated products. Okay, more concentrated product in your liquid solution, which has an exponential effect on viscosity. That relationship is not linear; it's quite exponential. So there's a lot of pressure to use high viscosity materials in these devices. Again, putting a lot of pressure on this back pressure. That's not. The other problem, though, we have is that, of course, the people who make these needles aren't perfect either. So, you know, the needle IDs aren't exactly the same every time. And if you look at the gauge tables, these are the standard gauge tables for needles, you can see that a 27 gauge needle, which has an average ID of 0.21 millimeters, also has a tolerance of plus or minus 0.019, or nearly 10%. Okay? So, if you have 10% error in your inner diameter, and it's a d to the fourth, you could have a 30% variation in your back pressure, which is a lot of variation, okay, in your dose time, especially for auto-injectors, because that's supposed to be totally automated. So that could have a big impact on the variability of the patient experience. Big variability. So it's not good. So how do we deal with this? So can we come up with a system where we actually are able to deal with this force problem, but not compromise patient safety. That's the provocation. And here's how we do it. We use a tapered needle instead of a straight cannula. So by using a tapered needle, what you do is certain part of the needle on the one side, away from the patient, is still, if you like, the fat part. So there, the pressure drop is going to be that bit less. And it's only the little bit that gets into the skin that has to be the small part. So the patient experience can be good, and you've taken a significant, or potentially you've taken a significant bite out of the pressure, the back pressure. But the question is, how much? So we build a COMSOL model to do that. We model the system, 2D axisymmetric, and very hard to get the details here because the needle is so long, but you can kind of get the idea here. When I do 2D axisymmetric models on a fast computer, I tend to be very lax with the mesh, so I make it very, very dense. See, this mesh is far more dense than it really needs to be, but I can do it, so why not? From that, then, you can actually get a lot of interesting data about the behavior of the liquid in the system. And finally, we can check to see how well the model works in terms of the experiment. So this is the first data we generated. You see it here. Not too bad, actually. Doesn't look too bad. A bit of scatter in the data. But here was the worrying part. If you draw a 45-degree line, the data should fall on a 45-degree line, and it doesn't. Okay, so what's going on? Now, at this stage, you might say, oh gosh, we just got a bad model. Let's throw it out the window. But we knew that this is laminar flow. The geometry is a little bit complicated, but not that complicated. We've got everything. This shouldn't be as bad as this. We expected a lot better results. So we went back and we analyzed the data. When we saw this bias, we said, well, what could be causing this? Well, we did a bit more detailed analysis, and what we found was that the guy who was doing the experiment didn't control the temperature that well. He didn't pay much attention to it. Unfortunately, temperature and viscosity in this case are highly related. So the bias actually was a function of viscosity. So what we did was we repeated the testing with more attention to the temperature and hence the fluid viscosity. And we ended up with this. So that has an R-squared of 0.9977. I'll take that. Okay? I'll run with that one. And also, the slope of the graph is 0.9757. So, just 2.5% of bias. I'll take that. I'll run with that one. So this was considered to be quite successful. And the vendor of the needles was quite impressed with this. They didn't think we could ever get this kind of accuracy. So, if you think about it, then what we found was that the tapered needle reduces the pressure drop by 40 to 50%. That's huge. That's absolutely huge. There's excellent agreement between the model and test results. That means we have a system that we understand. That gives you the confidence to go out and make these things. We know the performance is sensitive to viscosity. That's good to know. We kind of knew that anyway, but now we know it even more. But what it also tells us, because the R-squared is so high and the scatter is so low, it's telling us something that the manufacturer actually claimed, and we didn't really believe him at first. He must have, unless he's cherry-picking these needles, he actually has very good control of his manufacturing process. Now, we don't know what his manufacturing process is. It's proprietary. He guards it like Fort Knox, as he would. It's his IP. Okay, we have an idea of what it looks like, but it's not something they talk much about. However, this data would support the fact, unless they did a good job of cherry picking, that they do actually have very good control of their manufacturing process. So the variability in ID is quite small. And so all our major effects have been captured in the model, so we can extrapolate to confidence. And I suppose the icing on the cake is that this needle, which was a concept when we worked with the vendor, they now have this commercialized and sell it as a needle, an actual tapered needle, which I think is quite an impressive manufacturing feat, that you can make a needle like that, high speed commercially, and make money out of it. That's pretty impressive. Don't know how they do it, but it's pretty impressive in my book. So this was a good project. Again, the nice thing about this project was it's not from a modeling perspective, it's not the most sophisticated thing you're going to see here at this conference, but it was hugely effective. And simple and effective makes my life an awful lot easier, and probably would make your lives an awful lot easier too. So, every now and then we've published some articles, and I've just included this here, just more in general modelling about success stories we've had. I just include them there if you get the things, you may be interested in looking at them if you get these slides. And that's really all I had to say. I don't know if we have time for questions.